So this will be the last section of content. From here on out, I mean, we'll still take a test. We still have a test coming. But after that, it's just like we're going to do targeted AP review or AP prep. So I have practice exams that we'll work on. We'll go back and reteach stuff that we feel kind of shaky about specifically. But that's going to be kind of the finish route. And I think, as I mentioned last time, the test format for this final test will have an in-class portion based on Chapter 9 content, and then a take-home portion based on the Chapter 7 stuff. So the take-home portion, you'll get a group of 3 to work with. So if you want to try to figure out who that's going to be in advance, you're welcome to do so. You guys can pick your own group of 3, no more than 3, no less than 3. There's 21 of us here in the class, so that's 7 groups of 3. That's what I wrote for. So, you know, and then the following week or so, next week is kind of, we're just going to do some AP stuff for the people that are gone on Cairo so they don't have to scramble to make anything up. We'll do the test the following week once they're back, and then do the take-home thing. Does that sound pretty good to everybody? Fair enough? Okay. Before we dive into 7.8 here, does anybody have questions from previous homeworks or anything else that we want to talk about here before we dive in? Okay, fair enough. So what we're going to be looking at in section 7.8 are called improper integrals. Essentially what that means, remember when we find an integral, we're talking about the area under a curve. So what happens if that area appears to be infinite, right? So like what if we're doing the integral from 1 to infinity of 1 over x squared? Well, the graph of 1 over x squared looks like this. That looks like that's curve goes on forever. That looks like a, how am I going to calculate that area if the end of the figure never ends? Or if I go from 0 to 1, where you're at like an asymptote, like that's still an infinite area to try to compute. So there's kind of 2 different types of these improper integrals. There's the infinite ones where one of the bounds is in infinity, and then the ones that are tougher to catch, which are the ones that are at a vertical asymptote. So we call those like a discontinuous integral. So it only matters if it's at a vertical asymptote. If it's at a jump or a hole, those don't matter. You can just integrate as if the hole's not there, or you can just integrate as if, at the end of from this jump and then the start of the next, like you can just do it exactly the way you would think. Works just fine. As long as there's finitely many holes, integration is, you can treat it as if there are no holes at all. If there's infinitely many holes, well, then that's a horse of a different color, and that's well beyond the scope of this class or really any, undergraduate calculus course, to be quite honest with you. But that's the idea of what we're going to be doing today, is working on how to do these sorts of problems. Now, keeping in mind, some of these problems, the answer is going to be infinity, but some of them not. Some of them will converge to an actual real number, even though the area appears to be, the figure appears to be infinitely long, but it might have a finite area. So let's just go ahead and dive in here and do an example. So let's say we want to do the integral from 1 to infinity of 1 over x. And we're asking to determine whether this is convergent or divergent. Convergent just means it has like a whole number answer, like a real numbered answer. Divergent means that the answer is infinite, either positive or negative infinity. So the idea here is that we're going to turn this since we know we can't plug like an infinity in, we're going to just turn this into a limit problem. Or instead of the integral from 1 to infinity, we're just going to do the integral from, or the limit as t approaches infinity of the integral from 1 to t. Everybody's okay with that? Now we can treat this exactly like we would before. So the antiderivative of 1 over x is, natural log of the absolute value of x. Everybody feel good there? Okay, so that's the limit as t approaches infinity of the natural log of t minus the natural log of 1. Now I dropped the absolute value. Why was I able to drop the absolute value here? Right, t is never negative. It's going from 1 to infinity, dead on. So the natural log of 1 is just 0. So we're just left with the limit as t goes to infinity of the natural log of t. And what is that equal to? Do you remember what the graph of the natural log of x looks like? All right, that's basically the graph of the natural log of x. So it's the limit as the x goes to infinity. Infinity, right? Because this arrow is just still kind of moving up. Everybody agree? So what do we say here? Divergent. Everybody feel okay with the process? Fairly straightforward. We're just going to replace the infinities or anywhere where there's a vertical asymptote with a t and just do the limit, as t goes to whatever the value is. And then, everybody so far so good? Okay, let's just kind of keep doing numeric examples. So the next one here is the integral from negative infinity to 0 of x e to the x dx. So my first order of business is going to be to replace that negative infinity with a t and make it a limit problem. And again, there's nothing specific about the letter t. You could use whatever letter you wanted. Right, canonically, we typically use t, but if the problem had t's in it, I don't want to do that. So how do I do the integral of, or find the antiderivative of x e to the x? U sub's not going to work here, right? So what do we do if U sub doesn't work? Integration by parts is probably the likely choice. So we're going to start by picking our u and our dv. The u is the function that gets simpler when you differentiate, and the dv is the one that should be easy to integrate. What should I pick for my u? X, very good. And my dv should be e to the x dx, right? So du is just going to be dx then, and v would just be e to the x, right? Because the derivative of x is just 1 dx, and then the integral of e to the x is just e to the x. So if I do my integration by parts, the formula is u times v minus, what did I forget here? Still have my limit there. And then it's u times v, but evaluated from t to 0 minus the integral from t to 0 of v du. So far, so good. Okay. So the antiderivative of e to the x is just e to the x, right? So I'm going to have x e to the x minus e to the x evaluated from t to 0. So now let's plug some stuff in. So we have the limit, and maybe even I think about this as like that. That might make things a little bit simpler. You don't have to, though. So we're going to go from the upper, which is e to the 0 times 0 minus 1, minus e to the t times t minus 1. Everybody feel okay with what I did there? So that's going to give me the limit then as t approaches, that should be negative infinity. How have I not been carrying that through? Probably have to go back and change that. So negative 1 minus t e to the t plus e to the t, right? Let's go back and change all those negative infinities. Gosh, I did it right at the start too, didn't I? All right. So the negative 1, when I take the limit of that, nothing changes, right? Not entirely obvious what that's going to be. But what's the limit as t goes to infinity of e to the t? So remember, the negative infinity is going to make it like 1 over. And as x goes to positive infinity, that's going to go to 0, right? Now, the problem is if I try to do that same thing, this is going to be like infinity times 0, right? Remember what that is? That's an indeterminate form. What did we have to use if we have to take the limit of an indeterminate form? L'Hopital, yeah. So what we'll do is I have to rewrite that now as like a fraction, right? So I could do that. If I L'Hopital that, everybody feels okay, which is just going to be 0, right? Everybody feel good there? Because when I put the negative infinity into the exponent, it becomes like e to the huge. 1 over huge is just 0. So my answer here is just -1. Does that feel okay there with what I did? So don't be surprised if you have to bust out like a L'Hopital at the end to sort through the limit pieces. Michael? So to use L'Hopital, it has to be written as a fraction. So like e to the t just becomes 1 over e to the -t. And that allows me to put it in a fraction. And I prefer to do that over like making it e to the t over like t to the -1. Because when I differentiate that, it doesn't go away. Like I'd rather have the e to the t in the top, or the t in the top, because when I take the derivative, it's just gone. Does that make sense, Alex?
How did you get the negative into the root?
So I did the derivative, right? Because I'm doing L'Hopital's rule here.
Yeah.
So the derivative of that, I have to do a chain rule. That's where the negative sign pops in. Is that cool? Okay. You guys feel all right so far? This is kind of the gist of it, is just kind of like doing these kind of problems. The worst part is usually the integration. Let's do another one. Myself a little bit of space here. So what do you notice about this guy here? So I have infinities at the top and the bottom, right? So I can't do one of these improper integrals where I have two problem parts. So what I'm going to do is I'm just going to do this and break it into two separate integrals. And it doesn't matter what the constant is that I use to break it into two separate integrals. But like 0 is an awfully nice number to be plugging in. That seems like a good choice to me. But you could have used 1 or 7 or 14,382. Like, it doesn't really matter, but like, don't make your life harder than it needs to be. Like, just use like a 0 or something simple. Everybody feel okay here? So after doing that, I can do like the limit as t goes to -infinity of the integral from t to 0 of 1 over 1 plus x squared dx plus the limit as, let's say, w goes to positive infinity of the integral from 0 to w 1 over x squared dx. Everybody feel good here? So far, so good. How are we going to integrate, or what's the antiderivative of 1 over 1 plus x squared? Tangent inverse. Well done. So this is going to be the limit as t goes to -infinity of tangent inverse x evaluated from t to 0 plus the limit as w goes to positive infinity of tangent inverse x evaluated from 0 to w. Everybody still feeling okay? Now do my definite integral definition. So this is going to be limit as t goes to -infinity of tan inverse of 0 minus tan inverse of t plus limit as w goes to positive infinity of tan inverse w plus tan inverse 0. Everybody feel so far so good? So tan inverse of 0, that's just 0, right? And the limit of 0 is just 0. So far so good? Anybody know what the limit as t goes to infinity of tan inverse of t looks like? Do you remember what the graph of tan inverse looks like? Well, that's tangent, right? So tan inverse looks like this. So as we go to negative infinity, we're just going to negative pi over 2. Use the green. And as we're going to positive infinity, we're going to positive pi over 2. Everybody feel good there? So this just turns into pi. Pi over 2 plus pi over 2. You guys feel okay there? All right. I'm going to do one more. I'm just going to do 5. We're going to call this, well, okay. Let's do 5. Now, there's nothing on 5 that makes it look like it's going to be an improper integral at first glance, right? Because the bounds are just 2 and 5. But what do you notice, Lucas? I mean vertical asymptote at 2, right? Because if I plug 2 into the denominator of that function, you have a 0 denominator. You guys catch that? So we're definitely going to have to replace that 2. Everybody feel okay there? You see why we had to do that? Okay. To do the antiderivative of 1 over the square root of x minus 2, we should do a u sub, right? Where the u is going to be x minus 2, so du is just going to be dx. So really what we're taking the integral of is u to the negative 1/2 du. Everybody feel okay there? Now, a lot of the times I'll switch the bounds in terms of u's. I probably don't do that with an improper integral. I'll probably just substitute back in my x's at the end so I don't have to muck around with like, you know, like t minus 2 or something in my integral. Like it just, or in the bounds of my integral, that's just kind of stinky to deal with. You can, it's fine. I just prefer not to. So this is just becomes 2 u to the 1/2, oops, limit t goes to 2 of 2 u to the 1/2 from t to 5. And then let's plug our u back in. And now we're ready to just evaluate. Good there. That's supposed to be a 2. What's going to happen here when I plug the 2 in, or when I try to do the limit as x approaches 2 here? I can just direct substitute that, right? What do you guys think? Okay. I want to point out a couple of shortcuts now. So the first shortcut I just cruised past and didn't talk about. But if I have the integral of the integral from 1 to infinity of 1 over x to the p dx, that integral is going to be convergent if that p, the exponent in the denominator, is greater than 1, and divergent otherwise. You say, okay, that's great. How is that helpful? Well, if I combine that with the comparison test, which I'll drop in here, it provides a great thing to do a comparison with. So suppose that f and g are continuous functions where f of x is greater than g of x, which is greater than 0. If that is the case and f of x is convergent, then g of x is convergent. Or if g of x is divergent, then f of x is divergent. So, for example, on this problem back here, I could split this at 1. So I could use the comparison test because 1 over x squared is less than or equal to 1 over 1 plus x squared. Greater than or equal to 1 over 1 plus x squared. So it's like an easy comparison test to know right away whether it's convergent or divergent. And if it's divergent, I don't even have to do the integral. I can just use the comparison test and done, and skate away free. Everybody, do we feel okay on that? So the idea here is that 1 over x squared is greater than or equal to 1 over 1 plus x squared. So this is like my f, and this is my g. Since this is convergent, I know what this one is convergent right away by the comparison test. Does that feel okay? All right. For problems here from this, I think you guys can just work on like 5 to 23. Should be odds. All odds. Here, let me double check to make sure that's what I put in. I said 5 to 39. That seems like too many. I'll update that and just make it 23. That seems sufficient. Oh, now I said 27 on this document. Boy, I got myself all confused here. That seems fine. We'll just make it 5 to 27. And I'll update this thing. But that's the gist of what I have for you this year. This is like, I would say what we've done this calendar year is essentially calc like between 1.5 and 1.75 that you've done like your entire first year calculus course and then like a half to 3/4 of your second year calculus course or second semester calculus course. Hi, what's up? You look very purple. You're welcome. AP Calculus. Look at the reaction to that, guys.
Is it a fun class?
No.
Wait, Maria takes 2 math. You take 2 math? Yeah.
This is why Maria already knows all the calculus stuff we're doing in IB.
Yeah, I
It's
don't know
'cause-
what we're doing, so.
It's because it's easy.
Bye, Mr. Floyd.
Yeah. So that's it. That's the semester. From this point on, we have, you have some homework assignments to finish or some MyEP quiz stuff to finish, and then next week we're just going to do review stuff. And then the week after that, we'll take our final test. We'll have a in-class portion and a take-home portion. The take-home portion will be with a group. So by the end of next week, try to figure out your group of 3. And then, we'll give you some time to start and end that in class, and then have you take home, talk about it the week after next when everybody's done with back from Kairos or whatnot. So those Kairos folks that are going to be gone most of next week, it sounds like, right? We're just going to do review stuff, so there's no new content to be covered. I'll have the test description for the in-class portion up in the OneNote. If not, by the end of this week, certainly into next week. So when you get back from Kairos, you'll be able to see that. But I think I have that mostly hammered out. And that's the gist of it. That's the end of the semester. So like by the end of the week after next, like all the grades for this class will be in and done. If there's something you need to want to do for a retake, we'll deal with it at that point. But there should be plenty of time in those last 2 weeks or 2.5 weeks or whatever that we'll have left to get that sorted out. But basically, here we are. We did it. Yes, sir.
So like in 2 weeks we'll have a double test.
We'll put those in if you're doing the doubles and have everything kind of set, and you'll know where you're at. And, any of the review stuff, I don't see any point in attaching scores to them, right? Like, it's probably just less stressful for everybody. You know what I mean? But yeah, that's my plan. Does that sound pretty good?
Yeah.
Okay. So let's, I'm going to sign off here. This felt like 35 minutes.